So, calculus students, as promised, here's a look at question number 25. And one of the first things that might be worth noting is that the figure that they give is not nearly to scale. If you think about it and look at the values, you'll recognize that there's a lot of symmetry here, and you can employ that symmetry when it comes to computing values. But when it comes to doing the calculus, you have to do the calculus for all points in space and time, and then make substitutions later. So you want to be certain that you don't rely on symmetry to set up your calculus. And if we take a moment to look at all of the possible variables that we might be working with, the only variable that we know remains constant is the rate at which the pipe is being pulled up to the building. Now, it should be clear that there's some right triangles in here that you can use to employ Pythagorean's theorem to relate these quantities. Let's look at how that might work. Since S and ds dt are part of the problem, then any problem triangle that we use is going to have S as its hypotenuse. Now, it doesn't really matter if you use the triangle that I just sketched or if you preferred to sketch the upper triangle that would have the same dimensions. So writing the Pythagorean theorem for this scenario and differentiating should be basically second nature at this point. So let's do an inventory of the variables, what we know and don't know. Well, first of all, x, we can compute x for the specific point in space and time that we're looking at. We don't know what dx dt is. We can compute y from the information we're given. We don't know what dy dt is. We can compute s, and we do know what ds dt is. So we're faced with that situation we faced so many times before. We have too many variables, and the way that we're going to work ourselves out of that is to find a secondary relationship to relate the variables that we have. So if we think about what I've defined as this problem triangle, over time, that triangle is going to be changing shape, and it's going to be getting smaller. There's a relationship between x, y, and s that describes that change. But there are other triangles in this problem that are also changing shape, and we can tap into those other triangles to get a secondary relationship that still relates to x and y. How will we do that? I think the easiest triangle to see and work on is this triangle. Now, in the same way that as the pipe gets pulled up, the problem triangle that we were working on gets smaller, this triangle is going to be increasing, at least in height, as the pipe is winched up to the top of the building. So we can set up a set of relationships between x, y, and r that describe the relationships in this triangle. So I'm writing this equation in purple, and I'm doing it for a reason, and that is to consider x, y, and what I'm going to call r. So first of all, the x in this problem triangle, is that the same x that would be in the problem triangle, in the original problem triangle? And the answer is yes. So I'm going to change that to red, just indicating that that is the same x. Now, when we look at this purple triangle, this y, is that the same y that we're describing in the original problem? And the answer is absolutely not, because that y was the height of that triangle that contained s and ds dt. This is a different y. So this y can be written in terms of the blue y, because we know that the height of the building is 12. So this purple y can be written as 12 minus the other original y, and then squared. And that, of course, is going to equal, and in this case, r is constant, so it's going to be 12 squared. So wrap your head around that for just a sec. Now that we're referring to the same x's and y's that were in the original problem triangle, we now have what we need in order to relate dx dt and dy dt to eliminate one of the variables. And, of course, we're going to differentiate. So differentiating that relationship, this is in the purple triangle, and doing a little bit of algebra, we can isolate either dx dt or dy dt, and I think I'll choose to isolate dx dt in this case. And after isolating dx dt, our next step will just be to substitute that dx dt into the problem triangle, and then we'll have everything in terms of x, y, dy dt, s, and ds dt. So there will only be the one variable then, and that will be dy dt. Now, the algebra is going to get kind of messy, but it's a fairly straightforward process. And then, of course, we'll have to isolate dy dt. And after a bit of algebra, we have this expression for dy dt. So now we can make substitutions that will fix this to a single point in space and time, and ultimately compute that the rate of change in the y direction at that point in space and time is negative 0.2 meters per second. Now, in order to compute dx dt, we just have to go to a relationship between dy dt and dx dt, and as it turns out, we can tap back into this relationship because it's the easiest relationship that we have that we can use to compute dx dt. And when we substitute, then we find, aha, we're going to need to compute the value of x. So it's time to go back to the original problem and make that happen. So if we go back to the original problem, we can compute x, and x is going to be the square root of 108. So we can make that substitution. And now we have a value for dx dt at that specific point in space and time. So this was a very meandering sort of problem. You would not see a problem like this on the AP exam, but it certainly does make you think a lot about both the geometry and the math for this problem. Several students had questions about question number 29, and I think it's probably worth looking at the setup for this problem. Now, as with all these Pythag problems, it's all about finding that problem triangle. There's going to be a right triangle in there somewhere that you can use to relate the quantities you know and the quantities that you don't know. So on this figure, I'm going to add all the information that I'm given in the problem. So when I relate these quantities to the figure at hand, I get something like this. Now notice that dx dt I listed as negative 25 feet per second, because if I'm considering this distance right there to be x, then that distance is getting smaller as the runner advances, therefore the rate at which it's changing is negative. Now this is the kind of context that you're going to be responsible for, not only in homework type problems, but on the AP exam as well. The context being recognizing if a rate is negative or positive based on the scenario. And so finally, they're asking for what quantity. They're asking at what rate is the player's distance from home plate changing. So I'll begin by just making a line segment from the runner to home plate. I'm going to label that segment h, and the rate at which that length is changing would be dh dt. And so when we look at the problem, we should recognize, aha, dh dt is the quantity that they're asking us to compute. So now we see a right triangle, and once you see the right triangle, things should be really straightforward after that. So question number 47 had a few questions as well, so let's take a look at least the setup, because there are two perfectly valid ways of solving this problem, and for some people, one will resonate more with them than the other, but either is perfectly fine. So let's take this scenario and let's write down everything that we know. So as we consider this ice melting, the volume is going to be changing, so that's going to be a variable. We need to leave it in our computations when we're doing the calculus. The surface area is going to be changing, and the radius will also be changing. So these have to remain variables in our calculus, and later we can make substitutions when we take our calculus, good for all points in space and time, and narrow it down to a single point in space and time. Now, that single point in space and time is going to be when the radius is 10 feet, so we can, at that point, calculate the volume if we need that. We can calculate the surface area, and of course we know what the radius is at that particular point in space and time. So I think one of the simplest ways of thinking about this problem is just think about how we do every other problem. What calculus quantities do you know, and what calculus quantities are you trying to determine? So we know dv dt, and we're trying to determine the rate of change of surface area, which I'm going to call dsa dt. So if we're given dv dt, we're trying to find the dsa of t, then we need an equation which has v and sa in it. Once we have that equation, then whenever we differentiate, that v is going to give us the dv dt relationship and the dsa dt. So we know that there is a relationship between the volume and the radius. We know that there's a relationship between the surface area and the radius, but ideally we'd have a relationship here that related the volume and the surface area. Can we get there from here? And the answer is yes. This is just a system of equations, and if you think about SA over here, if we could compute R, or solve for R, it would have the SA variable in it. And then if we took that R and we went over to the volume equation and made that substitution, then we would have volume in our equation, and we'd also have the surface area in the equation. And then we'd have something to differentiate in order to get our dv dt and our dsa dt. And when we do so, we end up with an equation here relating the volume and the surface area. So now it just becomes a matter of differentiating to get dv dt and dsa dt, and then making appropriate substitutions to narrow it down to the specific point in space and time that this problem deals with. Now, since we're going to be differentiating, it might be helpful to go ahead and just pull all the constants out to make one expression there, and then, of course, use rational exponents to describe the power of the SA, and then differentiate. So, when we've done that differentiation, then if we do an inventory of variables, we know what dv dt is. We can compute the surface area. That's for the time when the radius is equal to 10. And finally, dsa dt, that's the quantity that we're looking for. So now it just becomes algebra and substitution. Now, there's another approach to this problem. So, as before, we have the same scenario, and we should recognize that we're given dv dt, and we're asked to determine what dsa dt is. So there's the crux of the problem. So if you just start thinking in terms of dv dt, since that's given, you could differentiate the volume equation for the sphere and find an expression for dv dt. Well, that's all fine and dandy, but I don't see any dsa dt. But proceed. Let's do the same thing with the surface area. Differentiate the surface area equation, since you know that that's the quantity that you're being asked to compute, and you get an expression for dsa dt. Now notice, dv dt is related to dr dt, and dsa dt is also related to dr dt. And if we just started the inventory of values like we do so frequently, consider what we know in that volume equation. We know what dv dt is, we know what r is, and we don't know what dr dt is. But we could certainly compute dr dt because that's the only unknown in that equation. So if we did determine a value for dr dt, does that help? Well, let's go to the answer side of things. You want to determine the surface area, or the rate of change of surface area, rather, with respect to time. And what quantities would you need to know to compute that value? Well, you would need to know R, which we know, and you'd need to know dr dt. Well, initially you don't know dr dt, but if you did compute dr dt from the dv dt, then you could make that substitution. And when you did, you'd have all you need to compute dsa dt for that specific point in space and time. So the idea here is that R is like the go-between variable between the volume and the surface area, And as a consequence, drdt will be the go-between variable between the dv/dt and the dsa/dt. So if we did the algebra and the substitutions necessary to do that, then we would find that at that particular point in space and time, whenever the radius was 10, that drdt would be -9/160 feet per hour. And that gives us the quantity now that we can substitute to solve for dsa/dt. And voila, there's dsa/dt when r is equal to 10.